comes after project. That is, we will start with a relative motion, which is the final aspect of kinematics. Okay. So we will also apply relative motion concept to situations where we are looking at projectile motion, but it will be in specific situations as we'll discuss. So let's first understand what is the meaning of the term relative motion. Okay. Relative motion is the situation where we observe the motion or write the kinematical equations of a moving object in a moving reference frame or with respect to a reference frame which is in motion with respect to the ground. Okay, so the motion of a moving object as observed with respect to, or what we say relative to, a moving reference frame. So for example, if you look at a situation where one object is moving at a speed of 20 meters per second along a straight line like this, and another object going past it, moving parallelly, but at a speed of 30 meters per second. So VA and VB are with respect to the ground frame. Then in A's frame, the velocity of B with respect to A's frame will appear to be how much? Can you tell me? Anyone?
The 10 meter per second.
10 meters.
That's correct. It will appear to be 10 meters per second. So this term is now called the relative velocity of B with respect to A. Okay, so this is an example of the application of the concept of relative motion. Okay. Another example is if you observe vertically falling rain, but with respect to the reference frame of a fast moving vehicle, a vehicle moving fast on the horizontal surface. If you observe vertical rain from inside such a vehicle, how the rain appears to be, it doesn't appear to be vertical anymore. It appears to be hitting the windscreen slanted. And faster the vehicle is moving, the more that slant appears to be. So that is another example of the concept of relative motion.
So in the above example, the AB will be minus 10.
Yes, that's correct. Okay. Velocity of A with respect to B will appear to be -10. So if you're sitting in the vehicle B, A will appear to be going backwards with respect to you at 10. If you're sitting in A, then B appears to be going forward. Okay, so that's so vertically falling rain appears to be slanted when observed from inside a moving vehicle. This occurs because the velocity of raindrops relative to the frame and the reason for that we'll discuss by the end of today's lecture. You'll understand why that happens. So this is a general definition and couple of everyday examples of the observation of relative motion. Now to understand how to write the equations of relative motion, let's start by understanding the parameters of relative motion. Like we had started kinematics by defining and understanding the kinematics parameters like position, displacement, velocity, etc. So like that, we will again redefine all these quantities with respect to relative motion or for relative motion. We'll define what is the meaning of relative position, what is the meaning of relative velocity, etc. And when we say we'll define these, they will be proper vector definitions for general 3D motion.
Can you scroll up?
Yes, just a minute. Okay, so done with this part now. So let's understand each definition of relative motion parameters So like we had started kinematics by understanding position vector. Now we'll start by understanding relative position. Okay. So let us say that with respect to the ground frame, we have two objects A and B, which are individually located. So imagine a three-dimensional ground frame. So in the ground frame, a certain particle or certain body A is located over here. Let's say. Its position vector is RA, and another body or particle is located, let's say, here. Okay. Then the relative position of B with respect to A. This quantity we want to find out. This is the relative position that means we want to shift our origin from O to A so that A becomes our reference frame, and with respect to A, where is B located? So that is defined by this vector. You can see this quantity over here is described by the vector from A to B. Now you can see that these three vectors are forming a vector triangle such that this is nothing but RB minus RA. So this becomes the vector definition of relative position, where RB is B's position in ground frame, and similarly RA is A's position in ground frame. Okay. So this is very simple to relate. For example, if A and B are located in a two-dimensional XY plane at positions 1, 2 and 4, 3 in centimeters respectively, then so just apply this above definition. You will understand, practically speaking, how this works. Yes, very good. That's correct. Anirudh, Kirti, your answers are correct. Right. So you can, even without drawing a diagram, you can understand here that position of A in the XY plane, which is the ground frame, will become I cap plus 2j cap, and position of B will become 4i cap plus 3j cap. And therefore, position of B with respect to A, given by the formula RB minus RA, will become this minus this. So that is 3i cap plus j cap. And similarly, position of A with respect to B will be minus 3i cap minus j cap. So one thing you learn from here this is that position of B with respect to A is defined as negative of position of A with respect to B. These two always have an equal and opposite relation. Now we can easily understand this or interpret this result by just making a two-dimensional diagram here. It will work out quite simple. If this is your ground frame, two-dimensional XY plane. Okay, so currently in this, A is located somewhere over here. At 1, 2. So this is our position vector RA. And B would be located in comparison somewhere over here. So B's position vector would be like this. And hence you can see that the position of B with respect to A would be this. Or just reverse this. And the position of A with respect to B would be this. And that's how you're getting these results. Okay, now having understood this, the next thing we will look at, just like in kinematics, the sequence of parameters was after position we learned about displacement. So here also the second parameter we learn about is relative displacement. Okay. So earlier we have seen that in kinematics, we defined displacement as what? Change in position. It's the vector difference of final position with respect to initial position. Okay, so something like that here also. So in kinematics, displacement was defined as delta r, or final position vector minus initial position vector. So like that over here, relative displacement of, let's say, B with respect to A. So it will be defined as the change in position vector of B with respect to A. So that's the definition. Okay. This is the relative displacement that equals to the change in the relative position. Okay. Now we call that relative position was defined as absolute position of B in ground frame minus absolute position of A. So that means relative displacement, which is delta of relative position, is delta or change in position of B minus position of A. So it is change in position of B minus change in position of A, which means that this can further be reduced to change in position of B in the ground frame is nothing but displacement of B with respect to ground. Similarly, delta RA is nothing but displacement of A in the ground frame. So the relative displacement as a vector definition becomes the displacement of B minus the displacement of A. So that is why, for example, we will see that if something like this is happening, that we have two objects, let's say A and B like this at time t equal to 0. And then after some time, A makes a displacement, let's say of plus 2 meters. Okay. And during that same amount of time, let's say B makes a displacement of plus 6 meters. Then the displacement of B with respect to A here becomes how much? It becomes plus 4 meters. And the displacement of A with respect to B becomes minus 4 meters. Okay. So this result that you understand quite easily from the diagram, it is as a result of this definition here. This case, when we write it in one-dimensional vector form, this is plus 6 minus of plus 2. So that's how this becomes plus 4. Okay, now likewise, if we were to have a situation where two objects are moving towards each other, let's say initially A and B are like this at time t equal to 0, and then after some time E reaches here, having made a displacement of plus 2 meters, but this is at time t, whereas B displaces itself like this. Time t. So in this case, what will be the relative displacement of B with respect to A? And what will be the relative displacement of A with respect to B? Yes, very good. That's correct.
Sir,
Yes.
sir, the question is like that of pseudo force, right? Like we change the direction of the displacement.
Um, Actually, when we come to relative acceleration, you will see that pseudo force can be justified by the concept of relative acceleration. Okay, this is, I mean, just pertaining to that concept that you are looking at the motion of one object, but with respect to a moving reference frame. You understanding the point? No? Just think
Yes,
of it from a practical point of view. Like A and B are two moving vehicles, let's say, and you are sitting inside the vehicle A. Then to you, the displacement of B, for example, in the second case, the displacement of B will be like it's coming closer to you by 6 meters, not by 2 meters, not by 4 meters, because you yourself also moving closer by 2.
yes, sir.
Okay. So in this case, you will see that the displacement of B with respect to A will be minus 6 meters. Okay. Because this will be displacement of B minus displacement of A, which is minus 4 minus of plus 2. So that's how this will become minus 6. Whereas displacement of A with respect to B will be plus 6. Yeah. Now let's look at a two-dimensional example. So P and Q are located at the same position on a horizontal plane at t equal to 0. Now, after some time, P has made a displacement of 12 meters towards north, and Q has made a displacement of 16 meters towards west. So calculate the magnitude and direction of P's displacement relative to Q. So again, you can try out this question by just converting it to a vector equation or converting the given information into vector notation using some I cap, J cap, where you define your X and Y axis according to the geographical directions, north, south, east, west, etc. Or you can also convert it to a diagram, the given information, and from the diagram, you can geometrically draw the quantity which is required. Okay, but either way, you'll see that it's quite easy to understand relative displacement concept in this two-dimensional example. Yes, Kirti and Anirudh, as usual, again, your answers are correct. Only Kirti, if you're giving the direction in geographical terms, you have to also state the angle in degrees. Okay. So you have
Yes.
to say so many degrees, north of west or west of east or whatever. Okay. So let's understand this. Okay. So in this kind of situation, it is better to start with a geometrical picture. Okay. So let's say we take the origin as the original or the initial position of P and Q, and our x-axis is in the west to east direction. And our y-axis is south to north. Okay. Initially at t equal to 0, P and Q are both located here. Okay. Then what is happening is that the particle P is making a displacement towards the north of 12 meters. So P goes here. So displacement of P will be 12 j cap. Okay. And in the same amount of time, Q is making a displacement of 16 meters towards west. So Q is ending up here, minus 16 I cap. So now we can see that the displacement of, for example, P with respect to Q will become the displacement of P minus the displacement of Q. That will be this vector. And geometrically, you can see that this is 20, and this angle here is how much it is, 37 degrees. So you can see that the displacement of P with respect to Q is 20 meters at 37 degrees north of east. Or we can say that displacement of P with respect to Q is 16 I cap plus 12 j cap. Vector form like this. Okay, so hoping this particular example is clear to all of you. Now, naturally, we move on from displacement, we move on to the concept of velocity, like we had done in kinematics earlier. Now, only difference is we'll be talking about relative velocity. Okay, so next up, let's look at the concept of relative velocity. So previously in kinematics, we have defined instantaneous velocity as instantaneous rate of displacement with respect to time, or that's the same thing as instantaneous rate of change of position with respect to time. So likewise, the relative velocity of, let's say, B with respect to A can be expressed either as instantaneous rate of displacement of B with respect to A with respect to time, or can also be defined as instantaneous rate of change of relative position. Okay. Now further, we have seen that displacement of B with respect to A is displacement of B in the ground frame minus displacement of A. And likewise, position of B with respect to A is RB minus R. So this operator just applies to this whole bracket like this. It becomes rate of B's displacement minus rate of A's displacement, or you can express it as rate of change of B's position minus rate of change of A's position. So as you can see, whether we go with the left hand definition or the right hand one, this one or this one, either way, this is absolute velocity of B in ground frame minus the absolute velocity of E in ground frame. So you have a very symmetrical sort of series of definitions which are based on vector difference. The operation that we conduct vectorially is the difference of two quantities. So whether we are talking about relative position, it is a vector difference of the individual positions, or we are talking about relative displacement, is a vector displacement, vector difference of individual displacements, or now we can see relative velocity becomes VB minus VA. So through this now we can see, we can revisit those examples that we were talking about earlier. If A is moving at, let's say, whatever, 20 meters per second, and B is moving in this direction at 30 meters per second, then we can see that we can write VA as plus 20, write VB as plus 30 I cap, or in one dimensional form, we can just write this as plus 20 and plus 30. But on the other hand, something which is a common experience for us, that if two objects are moving towards each other, then the relative velocity's magnitude becomes more, becomes the sum. So here, so A's velocity will appear to be plus 50 from B's frame, and B's velocity will appear to be minus 50. So these are two oppositely moving objects along the same straight line. Whereas two parallelly moving objects, when we apply this vector definition, the relative velocity becomes the difference in the magnitudes of their velocities. Whereas in the second case, where they're moving opposite, it becomes the sum of the magnitudes. So these are 1D examples of the above equation.
Sir,
Hmm.
so for our next major test, what will be the portion from physics?
Kinematics full part will be there, beta, including relative motion. Okay. And probably part of circular motion also, which will be the chapter we'll do after relative motion. Whereas in the other track, friction will be there, beta.
So, but we have only like one class after this.
Yeah, so like I said, no, relative motion we'll complete today. And in the next class, we will complete problems of relative motion and probably introduction to circular motion. Circular motion is also in that sense, the first part of it is a continuation of kinematics, okay? Because it's another type of motion. Only difference is the path is circular. Okay.
Yes, sir.
So then what about friction?
Friction also you have started, no?
No, sir, it is starting.
No, sir.
Not yet started friction. Okay. So then only probably basics of friction will come. Like this week, you have had the friction lecture already or not?
No, sir. Today we are going to we have to discuss the assignments of Newton's laws.
Okay. So then probably friction may or may not come in the next chapter. You can clarify that with Hemant sir. Okay. But our part, like at least relative motion, too, will be included because relative motion will complete the theory and some examples today, and next lecture will complete the problems and more doubts. Okay.
So from kinematics to we have to solve anything or
No, it'll be only kinematics one so far. Relative motion is then kinematics one. Okay.
okay, sir.
So basically, we have to aim to complete the HC Verma exercise of kinematics before the next test, and also everything in kinematics from the first booklet. Okay, from the module one.
Kinematics 1 or kinematics 2 module?
Kinematics one only. Beta. Kinematics one itself has relative motion. Okay.
So I've solved the kinematics 1 module, but there weren't many problems of relative motion other than the in chapter exercise.
Yeah, so that part only. Na? And even in projectile motion, for example, there are some questions where you're observing projectile with respect to a moving object, or a projectile is thrown towards a moving object. So those kind of applications of relative motion. Okay. So don't worry, I'll explain what all you have to prepare. Okay.
And it would be great if you could tell the problems to solve from the module also.
Yeah. Okay.
So,
Uh,
so then,
Yes.
at the end of this lecture, can you also explain the case where projectile is thrown in a direction perpendicular to the incline from an inclined plane?
Matlab that is just like we have to apply the inclined motion concept only, but the angle will become 90 degrees. So in that case, what specifically happens is that if we take the x-axis parallel to the inclined plane, then our ux becomes 0 and uy becomes non-zero, and we just write the equations further like that. Okay, so we'll do a numerical example based on that, but the method is the same, exactly like we have seen for the projectile on inclined plane.
Okay, sir. So then relative motion of projectile is also coming, right, for the test?
Yes.
Okay.
Sir,
Yes.
sir, in the third line,
Ah,
in the notes part,
yes.
so it's written that differentiation of the
Hmm.
position vector B minus differentiation of position vector A. So it should be changed, right?
No, beta. See, velocity is rate of change, no? So this is see the second line here. It is rate of change d by dt of RB minus RA, no? You got it, no?
Okay.
So this operator now it goes inside the bracket, so it applies here and here. So that's how we get this term and this term.
Okay. Sir.
Okay, so now let's see a two-dimensional example. And for the two-dimensional example, we'll take the case we were discussing earlier about the relative motion of rain with respect to a moving car. Okay. Relative velocity of vertically falling rain okay, as observed from a moving frame. Okay. So if we have a situation that when we see in ground frame, what we are seeing is that the rain is falling vertically like this, such that the velocity vector of the rain in the ground frame, as it hits the ground, the velocity vector is VR. But at the same time, we are also observing that there is, let's say, a vehicle that is moving with a velocity vector like this, horizontally. Okay. So PR and PC are velocities of the raindrops and the car, respectively, as seen in the ground frame. So now if we change our reference frame so that we are observing this situation from the point of view of the observer who's inside the car, then what velocity the rain appears to have. Therefore, in the car's frame, the relative velocity of the rain droplets is how much. Okay, that is what we want to calculate. Exactly, that's correct, Kiti. But it's actually not southeast in that sense because south is in the horizontal plane. But are you understanding? It's vertically downwards and eastwards. Okay, so let's see how that calculation will be done. So velocity of the rain with respect to the car will be velocity of the rain in the ground frame minus velocity of the car in the ground frame. So if we draw these two vectors, you can see that velocity of the rain is like this, okay, and velocity of the car is a vector like this. They are perpendicular to each other. So as per the triangle law, the vector difference of these two is this vector. The velocity of the rain with respect to the car like this. So if this angle is theta, so to this observer, the rain will appear to be falling like this. He will see the rain falling in this sort of a direction. And you can see that the magnitude of this relative velocity will actually become square root of this magnitude square plus this square because they are perpendicular vectors. And theta, the angle of inclination, will be tan inverse of BC divided by VR. So this is the theta is the angle with respect to the vertical. As you can see, it is the slant angle with respect to the vertical. So from the formula of the slant angle, you can see that the faster the car is moving, the more slanted it appears to be. Okay, the rain appears to be slanted more and more steeply the faster the vehicle is moving. Okay, people, so hope this example is also clear to all of you. Now we move on to the final of the parameters for relative motion, and that is relative acceleration. And actually through this concept of relative acceleration, we'll understand another way to justify pseudo force concept that we've learned in Newton's laws. You'll see another way to understand why pseudo force appears, okay, and why the expression for pseudo force is like that, that it is opposite in direction to the acceleration of the frame and equal to mass into acceleration of the frame in magnitude. Okay, so let's understand this. So acceleration of a moving object B with respect to another moving object A, that is, as per the definition of acceleration, it is the instantaneous rate of change of relative velocity. Okay, so basically relative acceleration equals to the rate of change of relative velocity. And obviously we have seen that relative velocity is the difference of the absolute velocities or the ground frame velocities. So accordingly, the relative acceleration can be expressed as rate of change of VB minus VA. So again, this follows that same sequence of steps, and it gives you a symmetric definition like we had for relative velocity. By definition, the rate of change of VB is nothing but acceleration of B in the ground frame. The rate of change of VA is nothing but acceleration of A in the ground frame. So as discussed, we have a symmetric definition for relative acceleration. Okay, so now for example, suppose we have a situation like this, that the particle P moves in the xy plane such that its position at time t equal to t is given by 2t I cap plus t square j cap, where position is in meters and time is in seconds. Okay. And q such that the position of q at any time is 2t square I cap. Okay. So now find the relative displacement of P with respect to Q after, or you can say from T equal to 0, T equal to 1 second. Then find the relative velocity of P with respect to Q as a function of time. The value of this relative velocity at the instant T equal to 0 and T equal to 1 second. The acceleration of P with respect to Q. So this question will cover all the definitions that we've seen so far. And also it will give you some practice of vector algebra as well as calculus. Just try this out and send me the answers. Okay, people. So again, Anirudh and Kirti, let me verify the answers for you. Okay. So you can see that displacement of P from 0 to 1 second will be position of P at 1 second minus position of P at 0 seconds. So that you can see that position of P at 1 second is 2 I cap plus J cap, and initial position was 0 I cap plus 0 J cap. So displacement of P from 0 to 1 second is 2 I cap plus J cap. Similarly, if you look at displacement of Q from 0 to 1, so position of Q at t equal to 1 minus position of Q at t equal to 0. So if you do this, you'll get the displacement of Q similarly to be 2 I cap just. Okay. So the relative displacement of P with respect to Q from 0 to 1 second will come out to be the difference of these two. So it will just come out to be J cap. Okay. Then you can see from this that position of P as a function of time so velocity of P will come by differentiating this. So when you differentiate this, you will get 2 I cap plus 2t J cap. Similarly, position of Q as a function of time, this much. So velocity of Q will be 4t I cap. Okay. So from this now you can see the second part, the velocity of P with respect to Q. So velocity of P with respect to Q as a function of time is 2 minus 4t I cap plus 2t J cap. And from this you can look at the third part, velocity of P as a with respect to Q at the time t equal to 0. Just substitute t equal to 0 here. You'll see it is 2 I cap. Whereas velocity of P with respect to Q at the time t equal to 1 second. Just substitute t equal to 1 second here. So it will be minus 2 I cap plus 2 J cap. And these are both in meters per second. This is in meters. Now, as far as calculating the relative acceleration is concerned, we can now do two things. We can either calculate the individual accelerations, or we can also use the definition that this is rate of change of instantaneous velocity. So since we already got this, we can use this definition here. Or alternately, what we can do is we can calculate this acceleration. So from here, and likewise, we can do this also. So both the options are equally easy to calculate relative acceleration. Okay, so hope this is clear to you, people. Now let's look at another type of example where relative motion concept can be used. So what happens is that we have this elevator which starts at t equal to 0 with initial velocity equal to 0, but it has a downward acceleration of 2 meters per second square. And at the same instant, when the elevator starts falling, starts descending, a bolt comes off the ceiling of the elevator, and it's a freight elevator, so its floor to ceiling height is pretty large. It's 6 meters. So there is one observer who's inside the elevator. Let's say observer A, and another observer who's the ground frame B. So a bolt B comes off the ceiling of the elevator at t equal to 0 when the elevator just starts descending at uniform acceleration 2 meters per second square. So take g equal to 10 meters per second square and find first acceleration of the bolt with respect to the elevator's flow. Okay, so relative acceleration of the bolt with respect to the elevator's frame. Second, the time t at which the bolt hits the floor of the elevator. These two things we have to calculate over here. So just try this out, people. Take the value of g as 10, okay, that I've already given you here. Okay, so let's understand this. So what is happening is that acceleration of the bolt as seen from the ground frame is going to be minus g j cap, or acceleration of the bolt. Just write like this. It is g, or 10 meters per second square downwards. Okay, and acceleration of the elevator as seen from the ground frame is minus aej cap. So acceleration of the elevator we can write as 2 meters per second square downwards. So the first part, the acceleration of the bolt with respect to the elevator will be eight meters per second square downwards. If we write in vector form, it will be like this. So that's the answer to the first part. Now the initial velocity of the bolt is also zero. The initial velocity of the elevator is also zero. So the initial velocity of the bolt with respect to the elevator is zero. So displacement of the bolt with respect to the elevator will be half into 8 into t square downward. So when the bolt hits the floor, the displacement of the bolt in the elevator's frame is going to be h, or 6 meters downwards. So 4t square should be equal to 6. So t should be equal to square root of 6 by 4, or square root of 1.5 seconds. Something like this. Okay, people. So with this, we complete relative motion concept. Okay, we will see more examples in the next lecture. Now you can go on to complete H.C. Verma's chapter in kinematics. All the questions we'll discuss doubts from that in the next lecture, and you can also do relative motion questions from module 1 of kinematics. Also complete anything pending in projectile motion. That's it for today's session, people. Wish you all the best. Have a nice day.
So from kinematics 1 or kinematics 2 we have to solve?
Both better. Okay, but start with completing kinematics 1 first. Okay.
So kinematics 1 I have completed, so I can start with kinematics 2.
You can start with kinematics 2 in that case.
Okay, sir. So for the test, the module and H.C. Verma is enough, or do you have to solve more than that?
No, module and H.C. Verma is enough. Plus, I will send an additional worksheet in relative motion, like we're done in projectile motion. So once you've done that, that will be more than enough.
Okay, sir.
Okay.
So kinematics 2 has relative motion, right?
Yes, it has questions of relative motion also.
Yes.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir,
Okay, right. Yeah.
sir, I also had a clarification for one question from major test 4 mains. There was a projectile motion question. So can you please verify the answer for that? I'm
Okay,
not getting.
just send me the question on WhatsApp now. Later, I'll verify it for you. Okay, okay, madam.
Okay,
Send
sir.
me a screenshot of the question with the answer given. Okay, I will verify it for you.
Okay, sir.
Okay.
Thank you, sir.
Okay.
Thank you, sir.